Hello and welcome to helpyourmath.com. In this video, we're going to look at Pascal's triangle, specifically using Pascal's triangle and its connection to combinations. So, you know when you figure something out that is so basic and then it ends up being this hugely important thing that is celebrated for generations after you discover it? Yeah, me neither, but Pascal, he's pretty familiar with that. So, here's what Pascal's triangle is. The traditional triangle starts with a lone 1 in the top row. And then we create future rows by adding the two values that are directly above it in its position in the triangle. And this pattern continues and continues and continues, although we're only going to look at the first 13 of them. So it's a triangle and it starts out with just a single 1. And then the next row, we put underneath it the numbers that add up right above it. So there's nothing up there except for the 1, so it would be 1, 1. Then we go and extend and we say 1. We add up the two 1s in the middle, we get 2, 1. Here, there's only a 1 above it. This has a 1 plus 2, 2 plus 1, 1. Then we get 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1, and so on and so on. In fact, I have it very much completed, like I said, 13 rows here, so you can see what I'm talking about. And if you look at this, there's all sorts of patterns that you might notice. So go ahead, tell me some patterns that you see within Pascal's triangle. Did I guess you just talk to your computer? Because I definitely didn't hear anything you just said. I fooled you. Okay, well, some things we might see is that the outside edges are always 1s, right? I mean, that's always going to be because there's never going to be a different number there. You might notice this diagonal. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This one, if you're familiar with special numbers, these are called the triangular numbers. So triangular numbers are formed when you add the two, you keep adding one more. So 1 plus 2 is 3, 3 plus 3, 6 plus 4, 10 plus 5, 15 plus 6. So you keep adding one more number. Those are the triangular numbers. And on. There's lots of different things that you might notice. Those are some of the bigger ones. But something else that's really cool about Pascal's triangle is that it is combinations, which is kind of crazy. And we're going to look at some examples in just a second, but there's one thing we have to talk about with Pascal's triangle that's a little bit unusual. When we are labeling these, we call this a row, and this a row, and this a row. However, the top row is considered row 0, not row 1. So this is a very British thing, right? Because in England, they have a ground floor, whereas we have a first floor. So we're going to have to channel our inner Brit. So this is going to be row 0, then this one is considered row 1, this one is considered row 2. And the nice thing about this, you can always know what row you're in because it's always the second number. So this is the first row, this is the second row, third row, fourth row, fifth row, sixth row, seventh row, etc., etc. So the rows start row 1, the second row. So how exactly does this relate to combinations? Let's take a look. Let's calculate 8 choose 5. So we might remember the choose formula. If we have n choose r, that is n factorial divided by n minus r factorial times r factorial. So in this case, we would be plugging in 8 for n. That would be 8 factorial divided by 8 minus 5 factorial times 5 factorial. This would be 3 factorial. So we have 8 factorial over 3 factorial times 5 factorial. I'm going to expand the 8 factorial until I get to 5 factorial. So 8 times 7 times 6 times 5 factorial divided by 3 times 2 times 1 times 5 factorial. The 5 factorial is canceled. 3 times 2 is 6, and 6 and 6 cancel each other out. We're left with 8 times 7, which is 56. Okay, so we've determined that 8 choose 5 is equivalent to 56. Where do we see that in Pascal's triangle? And, whoa, wait, it might appear more than once. Let's see. Found it. Here's 1, and here's 2. And this is the only two places that I see a 56. In fact, that's interesting. Well, never mind. Okay. So I see the 56s, and there's 2 of them. How does this connect? Does it connect? One thing I notice is that, look, we're in the 8th row. So there's 8, okay? Do we have a 5 when we're dealing with anything? Now, remember how when we counted the rows, the top row is row 0? When we're counting the spaces in any given row, the first space we actually start with 0. So this is space 0, 1, 2, 3, 4, and 5. So what I noticed is that the 56 appears 3rd in the 8th row and 5th in the 8th row. Do you see how that might connect to this combination thing at all? Look right here, look at the denominator, 3 factorial and 5 factorial, 3rd and 5th. That's pretty crazy, isn't it? Let's try another example. In this one, we're going to do 11 choose 6. So 11 choose 6, that's 11 factorial, over 11 minus 6 factorial times 6 factorial. That would be, so this is 11 factorial over 5 factorial times 6 factorial. This would be, I'm going to expand 11 until I get down to 6. 11 factorial, that is, excuse me. Times 9 times 8 times 7 times 6 factorial. I'll expand 5 factorial, 5 times 4 times 3 times 2 times 1 times 6 factorial. Those cancel. The 5 and the 2, 5 times 2 is 10, so I'm going to cancel that with the 10. 4 will cancel with, well, it'll leave a 2 up in the numerator. And 3 will disappear if I simplify it with the 9. So then what am I left with? 11 times 3 times 2 times 7. So that would give me, if I multiplied this through, 462. Okay, do we see 462 anywhere? And maybe if you picked up on the last one, maybe we should look in the 11th row. If we go down to the 11th row right here, I see it right here, and I see it's right next to it. They're right next to each other. So let's see. Remember, we're starting with 0, 0, 1, 2, 3, 4, the 5th and 6th positions. So in the 5th position and the 6th position is where I see the 462s in the 11th row. And now you might notice, look right here. So 11th row, so the row is in the numerator, and then the positions are in the denominator. That's pretty crazy. And this is always going to be true. If we have n choose r, the n is referring to the row in Pascal's triangle, and the r is referring to its position in that row. Position in row. And this will always work for any combination, which is kind of crazy. Isn't that pretty neat? I think so. In fact, with these combinations, there's a lot of different things that we can do and a lot of things that we can do with Pascal's triangle. We're going to look at just a few more examples. So here's one. This is just a standard combinatorics question or a combination question. So a group of 5 undergraduates and 6 faculty members are involved in a research project. 3 people are chosen randomly to research in a school. How many committees can be formed? So always I encourage you, pause the video, see if you can come up with the answers by yourself, and then when you can check back with me. Okay, so how many ways could committees be formed? So we need 3 people from this research project. How many people are there total? There's a total of 11. So we're talking about 11 people. So we have 11 and we want to choose how many of them? It says 3. So 11 choose 3. I could do this the long way, but I don't have to because I have Pascal's triangle. The 11 means I need to go down to the 11th row, which is right here. And the 3 means I need to go to the 3rd position. But remember, we start with 0. So 0, 1, 2, 3. So 11 choose 3 would be 165. So there are 165 ways that this committee could be formed. Now, what if I get a little more selective here? How many ways could the committee consist of only faculty members? Well, there are 6 faculty members. So in this case, we would only be looking at these 6 faculty members. And this would be 6 choose. We still want 3 people. So 6 choose 3. Go to the 6th row. 0, 1, 2, 3. So 6 choose 3 must be 20. And lastly, how many committees would consist of exactly 2 faculty members? So this is a 3-person project, right? So 1, 2, 3. This is 2 faculty members here, which means the 3rd person must be what? This person must be an undergrad. So I'm just going to say student. So we have 2 faculty and 1 student. So the 2 faculty would be 6 choose 2. And the 1 student, well, there's 5 to choose from. 5 choose 1. What do we do with these? Well, this is a counting principle question, so we would end up multiplying the possible outcomes. So 6 choose 2. Here's the 6th row again. 0, 1, 2 is 15. times the one student, that's 5. So I need to go up to the 5th row, 0, 1. 5, choose 1. 15 times 5 is 75. So there would be 75 committees where there's exactly 2 faculty members. And what we have to consider there, and this trips up a lot of students, is that it's still 3 people. So I only give information about 2 of them. That third person still counts, and we just have to assume, or know, that that other person must be an undergraduate student. Okay, as of April 2020, the state of Colorado has 4 Republicans and 7 Democrats in the House of Representatives. 4 are chosen for a super secret special project. How many possible committees could be formed? Again, pause the video, see if you can answer these 3 questions. That was only the first question. There's 2 more. See how you do. Okay, well, this one's kind of boring because it turns out that 4 plus 7 is the same as 5 plus 6, like in the previous problem. Oops. Oh, well. So this one's going to be 11, right? Because we have 11 representatives total, and we're choosing 4 of them. So we're going down to the 11th row, 0, 1, 2, 3, 4. So if it doesn't matter what party they're affiliated with, then there are 330 possible committees that could be formed from these 11 representatives. How many ways could the committees have exactly 2 members from each party? So again, what this means is that we have to consider there's 4, 1, 2, 3, 4. This one we're going to say is 2 Republicans, and this one is 2 Democrats. What we'll do at the end result is we'll multiply them together. So 2 Republicans, how many Republicans do we have to choose from? There are 4, so 4 choose 2. And then 2 Democrats, well, there's 7, so 7 choose 2. 4 choose 2, that's the 4th row, 0, 1, 2, that's 6. And then 7 choose 2, 0, 1, 2 is 21. So it's 6 times 21, which would be 126. So if there was to be 2 from each party, there would be 126 committees of the 330. And lastly, how many ways could the committee have at least 2 Democrats? So this is asking a different question. There's 3 considerations here. At least 2 means 2 or more. So how many does that mean? We could have 2 Democrats, in which case there would be 2 Republicans, which we already know the answer. There's 126. We could have 3 Democrats, in which case there would be 1 Republican, which we need to calculate. And this is a 4, so we could have 4 Democrats and 0 Republicans. So we already know 126 of them. What about 3 Democrats and 1 Republican? That would be how many Democrats? 7 choose 3 times 4 choose 1. 7 choose 3 is, here's the 7th row, 0, 1, 2, 3, 35, times 4 choose 1, 4 is up here, 0, 1, oops, I was going to do a square, times 4, so that would end up being 140. So there's 140 ways there could be 3 Democrats and 1 Republican. How about this last one? We have 4, not 4. Let's try that again. 4 Democrats, there's 7 to choose from, so 7 choose 4. And Republicans, there are 4, and we want to choose 0 of them. 7 choose 4, 7th row is here. We'll do a triangle this time, 0, 1, 2, 3, 4, 35. 4 choose 0 is right here, and here's 0 times 1. So this would be 35. Now with these 3 numbers, 126, 140, and 35, we end up adding these together because this is like an or situation. We could have 2 Democrats or 3 Democrats or 4 Democrats. Anytime we use the word or with these types of questions, it's going to mean we need to add these values together. So 126 plus 140 plus 35 would give us a grand total. It looks like we have 301. Whoa, so there's 301 possible committees if we have at least 2 Democrats on this super secret mission. Okay, another application of Pascal's Triangle would be with specific types of probabilities. So a fair coin is tossed 10 times, right? So you flip it the first time, you record heads or tails. You flip it the second time, you record heads or tails, so on and so forth. How many ways could it land up heads exactly 8 times? This might not seem like a combination question, but it actually is, because what we're doing is we're flipping the coin 10 times, and we are choosing for 8 of them to land a specific way, specifically heads up. So this ends up being another application of a combination question, 10, choose 8. Where would we find this in Pascal's triangle? We're going to go down to the 10th row. 0, 1, 2, 3, 4, 5, 6, 7, and 8. The other thing I could have done there to save myself some time rather than starting with 0 is the end will always be whatever the row we're on. So this would be 10, 9, and then here would be 8. But yeah, we can also use Pascal's triangle or combinations for figuring out how many heads we could have in a certain number of flips. Another combination is subsets of a set. So in number theory, we discussed the idea of sets and subsets. A set A is a subset of B if all of the elements of A are in set B as well, right? So if set A is Monday, Tuesday, Wednesday, and set B is Monday, Tuesday, Wednesday, Thursday, Friday, we would say that A is a subset of B because I can find Monday, Tuesday, Wednesday in the set containing Monday, Tuesday, Wednesday, Thursday, Friday. Pascal's triangle can also help us determine the number of subsets of a certain size. So how many subsets contain 4 elements if we have a set with cardinal number 4? What this means is that we have, with a cardinal number of 6. What this means is that of the 6 elements, we want to choose any 4 of them to be in a subset. So we would say that this is 6, choose 4. That would be the 6th row down here, 0, 1, 2, 3, 4. And that would mean there are 15 subsets containing 4 elements. Pretty cool, right? Okay, how about the next one? How many subsets containing 3 elements can be formed from a set with cardinality 10? So that means of the 10 elements in the set, we want to choose 3 of them. We would go down to the 10th row, 0, 1, 2, 3. There would be 120. Ooh, I'm glad we didn't have to write that out. That would be a lot. But there are 120. How many subsets containing at least 8? At least 8 can be formed from a set with 11 elements. So at least 8, that's 8 or more. So that would be 8 elements or 9 elements or 10 elements or 11 elements. So this is going to be, remember I'm using that word or, so what we're really going to do is we're going to figure out each one of these and then add them together. This would be 11 choose 8 plus 11 choose 9 plus 11 choose 10 plus 11 choose 11. So all of these are going to be found in this 11th row. And if we work backwards, it might be a little bit easier because this one here, that's 11 choose 11, and there's 1, right? There's only one subset that could be formed with 11 elements from a set containing 11 elements, and that's just including all of the elements. 11 choose 10 would be the next one over. That would be 11. That's this one here. 11 choose 9 would be the one right in front of it, 55. And 11 choose 8 is the one right in front of that, 165. So if we add these all together, that looks like it's going to be 220, 230, 232. There are 232 subsets. That's a lot of subsets that contain at least 8 elements if we have a set containing 11 elements. Okay, and the last application that we're going to talk about in this particular video is binomial expansion. So binomial expansion is yet another application. It's so cool how many different applications there are. And what this will tell us is it will tell us what the coefficients are. So what ends up happening with binomial expansions is what we can kind of do is we take the exponent and we give the entire exponent to the first term we see in the binomial. And then we start with 0 for the second one. And then we lower the first one by 1 and we raise the second one by 1. I know that kind of seems weird. Now, how does this relate to Pascal's triangle? That's just setting up the variables. Pascal's triangle will end up being the coefficients. So this one particularly is the coefficient, the row that we would deal with is row 2. These would be the coefficients of the 3 terms if we were to expand x plus y squared. And you might know x plus y squared, right? Because we know it's the first term squared plus the product of the 2 doubled plus the second term squared. Well, when I talk about kind of like cheaty using the exponent, we would say that the first one gets all of the exponent, so x squared, and then it would be y to the 0, which is just 1. And then the the variables, we decrease the x squared by 1 exponent, so it goes down to 1, and we increase the y to the 0 up by 1. So we have xy, and then plus x goes down to 0, so it would be 1, and then y squared. The 1 to 1 is the coefficient, so 1, 2, 1. Which you can see looks just like that if we didn't put the ones there. Now, normally we don't put the ones there, but you know, you can if you want, but it's still the same thing. So for x plus y cubed, okay, we're going to write this out. So we start with x cubed and y to the 0, which we're not going to write y to the 0. Then we're going to decrease this exponent by 1 for the next term, and we're going to increase that y to the 0 by 1. So that's going to go up to 1. Then we're going to decrease this one by 1, so that's going to go down to x to the 1. We're going to increase this one by 1, so this becomes y squared. And then the last term, this is going to decrease by 1, it's going to disappear because x to the 0 is 1, and we have y to the 3rd. Now we're going to go to this row here, 1, 3, 3, 1. Those are the coefficients. So we end up with 1, 3, 3, 1. If we clean this up, what we would have is x cubed plus 3x squared y plus 3xy squared plus y cubed. And if you don't believe me, you can of course expand this. So you would expand this to x squared plus 2xy plus y squared, and then multiply that again to x plus y, and make sure, you can fact check me here. Make sure that you end up with x cubed plus 3x squared y plus 3xy squared plus y cubed. All right, just 2 more examples of these binomial expansions. Especially, I want to look at that last one because the last one does have a little trick because there is a number in it. So x plus y to the 6th, we're going to the 6th row, and we start out with x to the 6th. And then I'm just going to set up the variables, and then I'll come back and fill in the coefficients. So it's x to the 6th, then it's going to be x to the 5th, y to the 1st, x to the 4th, y to the 2nd, right? So the x's are decreasing by 1, the y's are increasing by 1, x to the 3rd, y to the 3rd, x to the 2nd, y to the 4th, x, y to the 5th, and lastly, y to the 6th. Now the coefficients are going to be 1, 6, 15, 20, 15, 6, and 1. Cleaning this up and kind of squishing it back together, we would have x to the 6th plus 6x to the 5th y plus 15x to the 4th y squared plus 20x cubed y cubed plus 15x squared y to the 4th plus 6xy to the 5th plus y to the 6th. Woo, that's way better than having to expand it. It's a lot of work, but it's way better than having to like multiply x plus y times x plus y 6 times. Okay, and last but not least, we're going to look at x plus 5 to the 5th, because this one's going to be a little bit trickier. So I'm going to erase this because we're done with that. We're going to the 5th row here. A lot of 5s in this one. This would be, so I'm going to do these at the same time just to save time. So we have 1 x to the 5th plus 5 x to the 4th, 5 to the 1st, plus 10 x to the 3rd, 5 to the 2nd, plus 10 x to the 2nd, 5 to the 3rd, plus 5 x, 5 to the 4th, plus 1, no x, sorry, get rid of x, 1, 5 to the 5th. So now we actually have to do a little bit more work because we have the 5s that were previously variables and now they're not. So the first one we still have x to the 5th. For the second one we have 5 times x to the 4th times 5, so that'd be 25 x to the 4th. The next one we have 10 times x cubed times 25, that would be 250 x cubed. Then we have 10 times x squared times 5 cubed. 5 cubed is 125, so this would be 1,250 x squared, plus we have 5 times 5 to the 4th, so that would be 5 to the 5th, and 5 to the 5th ends up being 3,125x, and then we have 5 to the 5th, so that would be 3,125, and that would be the binomial expansion of x plus 5 to the power of 5. This has been a lesson on Pascal's triangle and a variety of uses for it. Thank you for persevering through it, and thank you for stopping by.